Use StatCrunch to do things. Okay, well, what if we didn't have StatCrunch? What was the idea though behind the lesson that we were talking about last time? Okay, so we learned how to put things into a relative frequency and a frequency distribution, which technically meant we were putting it into what? A table or a graph? Table or a graph? Okay, so if we do a relative frequency distribution or a frequency distribution, we're kind of telling you that we want to put that in a table, right? Yeah. What was a frequency distribution? Summary of the raw data. It was the counts of the raw data, right? It was the frequency with which something was happening. Okay, that was our counts of the eye color. Okay. What was a relative frequency distribution? The proportion out of the whole, the proportion of blue eyes out of the whole class, the proportion or the percent of brown eyes out of the whole class. That's right. Okay. And what type of two graphs did we learn how to do? Or we talked about? Bar graphs and pie charts. That's right. When would I choose a bar graph over a pie chart? If I wanted to do what?
Compare.
If I want to compare two things to each other, 2 or 3 things to each other, right? If I'm trying to make a comparison from one thing to another, I tend to use you want to use a bar graph. And then what do we do when we're thinking of a pie chart? What's the use of a pie chart? Kind of getting a vision of that part or those parts out of the whole picture, right? You use a pie chart when you're wanting to look at the whole thing. That's why that problem, one of those problems on your classwork last week or Tuesday was asking you why the pie chart there for the student lunches or something like that was inappropriate. Right? You have that paper, get that paper out really fast. From Tuesday, right? It was on Tuesday. And I think it was question like 3 or 4 on the back of that paper. Okay. It's up outside of my office. You can get it after class. Okay. Question number 4. See that table right there? That's what kind of a table? What kind of a distribution is that in question number 4? Frequency or relative frequency? Frequency, right? The frequency distribution, because it's just the counts. Okay, and then it's telling you that there's something wrong with putting that information into a pie chart. You can look on the dance stuff. What's the matter with it? No, it's not because it's not put into percent.
You don't know the total amount.
Does it not add up to 100?
I know this.
I think it does. I think it does. This one's tricky. This one's not something that you're gonna probably get. But think about it for just a second. It's not the percentages. It's not that it's not adding up to 100. I think it does. It's not because it's not frequency, or it's not because it's frequency.
You don't know the number of people or the number of kids, or what is this name? Percentage of 4 to 6 year.
I think it's 4 to 6th grade students or 4 to 6-year-old students, or 6-year-old kids, something like that. No. Good guesses though. Y'all are thinking. I appreciate it. Why is this not an appropriate data set to put in a pie chart? No, that's right. We can't put quantitative data into a pie chart. This is really categorical, right? So we have 4 categories there. What are the categories that we're looking at?
Grains, vegetables, fruits, and saturated fat.
All right, grains, vegetables, fruits, and saturated fats. with a pie graph, you can't have overlapping categories. Saturated fats are actually in grains, fruits, and what was the last one?
Vegetables.
Vegetables. So you don't really know what amount of saturated fats are in grains or what's in saturated fats in fruits or how much saturated fats are in the other. So actually you can't do this in a pie graph because this is an example of when my categories overlap, okay? When we did our eye color, I can't both be a blue eye and a brown eye, right? It's one or the other. That was why, I don't remember if it was in this class or not, but you have to pick one. You get one choice, okay? It's one or the other. So if you're going to do that in a pie graph, pie chart, cannot be overlapping categories because you're trying to figure out what that percentage is out of the whole thing, okay? Now, Matt touched on another thing that we want to make sure that we understand, and that is those pie graphs and pie charts are only for what type of data? Qualitative data, right? Categorical data, okay? Categorical data. So what we're going to talk about today are, well, how do I go ahead and represent data that is quantitative? All right, so quantitative data, we specifically focus on that one today. So what we're going to look at is a distribution here. And I'm going to go to, and I have to log in here. So I'm going to go to a data set, and you can all follow along with me if you'd like to practice this. So here in StatCrunch, let me open StatCrunch up. I am going to choose the data set for US presidents. Okay, so I have here the data set for US presidents. It has 4 columns talking about the presidents, each one of those presidents that's on the left-hand most column. All right. And the one we're going to look at right now is going to be the age at inauguration. Okay, so the age of inauguration. Now, when we talked about summarizing or displaying, I should say, the data sets in qualitative variables, we first talked about that relative frequency and then frequency distributions, which were tables, right? So we want to come up with an idea of, well, how do I go ahead and summarize the counts for the data that we have here. All right, how did I create a table, in other words, for qualitative data? Where did I go in StatCrunch? For tables. Stat, tables, frequency. Okay, so we're going to choose the age at inauguration. We're going to let it default to the frequency and relative frequency distribution or statistics that you see in the center. And when I click compute, it throws up this pop-up and it says, whoa, that's a lot of unique variables there or unique values. Do you want to bin this? So when we look at quantitative values, remember those are values like that we can measure, and so that there would be a lot of different values for them. Think, for example, of the president's ages. If I were to tell you that the president's ages in that column right there range from 42 to 78, okay? So if I were to count up how many presidents were aged 42, how many were 43, and 44, and 45, all the way up to 78, that's a lot of different values, right? It's not just 5 easy, convenient categories like it was for eye color, was it? So what we're saying here, what StatCrunch is reminding you is, well, that's kind of a lot of numbers, individual unique values. Do you want to just go ahead and bin this or group it is what it's going to do. Just click yes, and I'll show you what that looks like. So here, we have the same type of table that we looked at for qualitative variables, only now it's quantitative. we had the frequency column there and the relative frequency column that still stand for the same concept as it did in qualitative variables or categorical. The frequency with which I have presidents' ages between 40 and 45 are two of them. There's two presidents who had ages between 40 and 45. Okay, and then we've got the next set. So what did they do here? They grouped the ages by what?
By 5.
They grouped them by 5. So when we're grouping them, it's called binning them, or you can also talk about putting them in certain classes. Okay, so the classes that they put these in is the same thing as binning them, which is the same thing as grouping them by a certain value. Okay, and so rather than seeing the unique values between 42 and 78, I'm going to group them into some categories. Now, StatCrunch defaulted to groups of 5. Okay, most of the time we're going to just let it be StatCrunch's choice what it's going to do because it's going to be very convenient. All right. Notice here that our frequency distribution says, okay, well now there's, if I were looking at the group between 45 and 50, there would be 7 presidents whose ages ranged between 45 and 50 and so forth. And then of course the relative frequency would be the proportion in which that was happening. Okay, so a frequency and a relative frequency distribution is not any different from our categorical data. It's just now with our quantitative data, we're going to bin the data, right? We got to group it so we can see it better. So the next display that we're going to talk about, or the next graph that we're going to talk about, is the graph that we typically use for quantitative values. And we're just going to look at the graph first. It's called a histogram. So if I go to graph, histogram, I want to select the age at inauguration, and I don't want to do anything else in here just yet. I'm just going to choose the age at inauguration as the column that I want to create a histogram for, and just hit compute and let's see what it looks like. So here is what's called a histogram. What does this look like? It looks like a bar graph, right? Now, it is not a bar graph. Histograms are typically drawn with their bars touching. Okay, so I'm going to say almost every single application you ever use to draw a histogram with, the bars will be touching. If you get in and you have to use Excel for some other class like biology or some other science or social science class, and you're running an experiment on data or something, and you use Excel, their histograms are going to show up and it's going to look a lot like bars, but it's not. Okay. So histograms for us are always going to have the bars shoved together. Okay. Now, this histogram, the bars are still going to be the same as what a bar graph is, right? The histogram, or the height of the bar, I should say, is still, since this was a frequency graph, the height of the bar still represents the total numbers in that category, or in that bin, okay? Or in that class, however you want to think of it. So remember, on our table over here, we said that there are 2 presidents' ages that are between the age of 40 and 45. And therefore, if I hover my mouse in that first bar right there, you'll see the same thing that was in the table, right? Okay, so the height of my bar represents the frequency of that category, or the relative frequency of that category, depending on the graph. Now, the next thing I want you to notice is, does everybody see in this little yellow pop-up, there's a bracket next to 40 and there's a parentheses next to 45. Everybody see that? Okay, does anybody know what that means? Those are mathematical symbols that actually have meaning for us. You remember what those mean?
Ordered pairs, right? Or no?
No, it's an interval. So for a bracket, when we see the bracket symbol, that indicates we can include the value. And with a parentheses, we cannot include the value. Okay, so what this is saying is we're gonna take and we're gonna include the number 45. We'll go all the way up to, but we're not in, what did I say? We're gonna include the number 40. We'll go all the way up to, but not include the number 45. Okay, why do you suppose that's the case? So it doesn't overlap. I can't count 45 in the lower column and count 45 in the next column, right? In the subsequent column. So we go all the way up to, but not include 45. It makes more sense when we have continuous data, right? Integer or discrete data, it's not nearly as clear as that. But if we had continuous data, that would be like decimal data. So I could go all the way up to 44.9999999 and not include 45. Okay, and then I go to 45 and I go all the way up to 49.99999, right? So that's considered a lower endpoint. All right, our bin has a lower value, a lower limit, I mean. And you can do either lower limits or upper limits, right? Typically, StatCrunch defaults to this lower limit. So I'm going to include the lower value all the way up to a stopping point. Now, let's do a relative frequency histogram. So if I go back to histogram, select the same column, only this time I'm going to choose relative frequency. You'll notice that if I put these two histograms next to each other, both of those histograms look roughly the same, don't they? If we're looking and thinking about the overall shape of this histogram, they are for the most part the same graph. All right, the scale on the left-hand side is a little bit different, so it throws it off just a little bit in your eye, but these are in essence the same exact histograms. Okay. Now, so you do the same thing for them, and they both are going to speak to us and describe the information and tell us the same thing. Whether you're looking at a relative frequency graph or a frequency graph, they both can give us the same type of information if I just want to discuss the shape of the histogram, which is what we're going to practice in a minute. Now I want to go back. I'm going to get rid of that graph right there for just a second. I'm going to come over here to the applet. And I'm going to open up this histogram with sliders. And I'm going to play around with that column of age for just a second. Because I told you that for the most part, I usually just let StatCrunch pick the size of its bin. So it grouped my data by 5s, which is fine. We normally want to let it just do that work. But what happens if I adjust what I'm grouping? So if I come down here to the bin width, and let's say I slide it down to 2, what do we have going on there? What happened? What?
There's gaps.
There's gaps. Okay. Why are there gaps? Is that all right? Can I still call it a histogram? I can. Okay. Why are there gaps?
You may not have been a president with those that were in the age range.
Whatever that group was, whatever that bin was, there probably wasn't a president who had an age in there. What else did it do by adjusting the size of our bin width?
Just broaden the whole data set on the x-axis.
Okay, it changed it. How is the graph on the left different from the graph on the right? Look at the bars. Are there more bars with the one on the right than there are to the left? And what else do we notice? Are the bars on the left skinnier or fatter than the bars on the right? Okay, so by adjusting the size of the bin, by adjusting what we group it by, right now I'm grouping it by 2s, aren't I? So I'm going to take the values between 40 and 42, and then the numbers between 42 and 44. 44 and 46, blah, 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 right? So I'm just skinny, I'm making my class width skinnier. And it changes the histogram. Now, if you're looking at kind of the overall shape here, right? The overall shape doesn't change that much. It's more of a personal preference, all right? So the bin width doesn't necessarily matter that much. I can take it up here and I can make it larger. You'll see that it's gonna make my bars fatter because I'm now encompassing more value within a single group, aren't I? Yeah? Shake your heads, yes or no? Yeah, you understand what's going on? Ask me a question about it.
I just don't know how to, it's not letting me look at the thing I'm looking at on StatCrunch.
So that's just a matter of pulling up StatCrunch. Do you have the data set pulled up?
She went here to the, you can click on the second one. And then go to my group. On the magnify glass. And then
Okay. While we figure out that back there, what I want you to see is when we are dealing with histograms, so on your paper right there, you need to write this down. When we are dealing with histograms, this is how they're constructed. You first have to go in and determine the class list, class width. Draw the rectangles. For each of those rectangles, understand that the height or the relative frequency of that rectangle, the height is the frequency or the relative frequency of that rectangle. Okay? And then again, the characteristics that we're looking for in a histogram is your bars need to be touching, and they would need to be the same width. So histograms are our preferred method. It's the method that we'll be using most in class is a histogram, and we use it. We construct these histograms using technology. Okay. All right, y'all got that written down?
No.
Okay. So histograms, determine your class width, draw your rectangles. The height is the relative frequency and the rectangles need to touch. Yes, Mary?
I was about to ask for a touch, but it means that's actually touching.
Yes, they got to touch. Yes.
But it's okay if you have like a graph that has gaps.
Yes, the gaps,
Considers those things as non-existent.
exactly. So gaps don't mean it's not a histogram. It simply means there's no data in that. Now I'm going to show you in a few minutes a histogram that is a histogram. It's not a bar graph, but it looks an awful lot like a bar graph. When we think of quantitative data, so maybe you need to consider this. If we're looking at quantitative data, that's when we're using and we're talking about histograms. Histograms are grouped or binned data, okay? As opposed to a bar graph, which is simply categorical data, right? In a bar graph, we have the categories along the bottom, eye color along the bottom. Here, in quantitative values or in quantitative data, the categories that are on the bottom are the bin widths, right? So our presidents are grouped by their ages of bin width 5, okay? Okay, so another type of graphical display that we're going to look at has to do with a stem and leaf plot. How many of y'all remember a stem and leaf plot from high school or earlier? So it would have been in Algebra 2 if you ever took Algebra 2. Do a blurb on stem and leaf plots. Also, they introduced this back into the curriculum. I think it's in the 7th grade curriculum now to do a stem and leaf plot. Does the name sound roughly familiar to any of y'all, even if you don't know what it is? Okay. All right. So a stem and leaf plot is another graphical display for quantitative values. And I can come down to, I can go to graph, stem and leaf. And again, I'm going to choose the age at inauguration for the column I want to look at, and I'm just going to hit compute. Let me pull up histogram one more time. I'll put those side by side. Look at those for a second. All right, if you squint your head and you turn your head, squint your eyes and turn your head sideways, does the 7-leaf plot look familiar? What's it look like? It looks like the histogram, doesn't it? Looks like the same shape as the histogram. Okay, if we were to, I guess, turn the histogram 90 degrees on its side, it would look the same as the stem and leaf plot. All right, so a stem and leaf plot is a fast way for us to take a data set, the set of the list of ages for the presidents. It's a fast way for us to take that data set and without using technology, create a histogram to represent the data. Because what we're going to see before class is over is I'm trying to look at the graphs, these histograms, because I want these histograms to tell me information just by the picture, and it will. Now, so our stem and leaf plot, can anybody tell me, so we have here a 4 and a 2, 3. We have a 4, a 6, 6, 7, 7, 8, 9, 9, 9, 8, 9, 9, 9. Can you tell me what's going on there? How do you think this is being constructed?
The first digit represents like it's in the 40s, and then the second after the column, it's like 42, and then 43 is in that row, and then we go down to 40, 46, 46, 47, 47, 48, 49.
So they took the ages of the presidents, right? And they let the tens place be on the left side, which would be the stem. And the ones place is going to be the leaf, technically, right? So for the first column, remember we said that, and by the way, it automatically grouped it by 5s, didn't it? Okay, so remember that we said in our histogram and in our table we created that for the grouping, for the bin between 40 and 45, there were 2 values, weren't there? We said that there were 2 presidents' ages that were between 40 and 45, yes? Isn't that what it said? Isn't that what we said? Okay. Now, the thing about a histogram and a table like that, when we group our data, we actually lose the ability to see the raw data within it. All right, so it's almost as if, you know, I know that there are 2 ages that fall here in that bar. I just don't know what they are. I know that they're somewhere between 40 and 45, right? Okay. So with a stem and leaf plot, I can actually see the individual data points. I can see the raw data. I can see that there was an age at 42 and an age at 43. Okay. So one of the advantages to a stem and leaf plot is I get to see the actual raw data. Okay. Another advantage to a stem and leaf plot would be that it's pretty easy to take a fairly short list, and this list was, I believe it's, I want to say it's like 46 data points in it, okay? So on a fairly small list, it's easy to construct a stem and leaf plot going through, all right? Now, you wouldn't want to construct this stem and leaf plot like this on a really large data set because that's not really time, it's not good use of your time. You would just put that data set into a technical software or something like that, and you would construct the histogram, okay? Another advantage to your stem and leaf plot is I can also see the smallest value and the largest value, which is the range of the data set, right? So I know the smallest value was 42 and I know the largest value was 78. Okay, so this is what's called a stem and leaf plot. And when you're looking at a stem and leaf plot, this is the information you want to consider about that. They're not always divided by their tens and their ones place. That's typically the way that I see it. You could also, if you had decimal numbers, you could separate it based on the decimal point. So the stem is going to be your leftmost digit you decide on, and the leaf is going to be the rightmost digit you decide on. It is basically a vertical histogram. You get to see both the raw data as well as our max and min numbers, the range of the variable of the data. But it's not exactly useful for really large data sets. It is a quick and easy way, however, to be able to see kind of just the general shape of our data. Okay, moving on. So we've looked at so far a histogram, which is our preferred method, and the method we're going to be using to look at data in this class for the most part using technology. We've looked at a stem and leaf plot, which can be constructed by hand fairly easily, and it still gives the same type of information as a histogram. And we have one more graph that we're going to look at here. And that graph is called a dot plot. Anybody know what a dot plot looks like? It would have been that same unit of statistics that you had when you talked about a stem and leaf plot. Okay, so a dot plot is constructed again using graph dot plot. Okay, graph dot plot. I'm choosing my age at inauguration. I hit compute. And I'm going to put that right above the histogram. This is a dot plot. So in a dot plot, again, a dot plot is not my favorite. I'll be honest with you. It's not my favorite because I kind of know what I want to get out of a graph for a histogram. And it does not always give me as much information as I think a histogram does, the dot plot. But it is, again, a fast way for you to take a small data set and manually plot the data to understand maybe what the distribution is or what the spread of the data is. Now, in a dot plot, each of the dots represents actual data again. So here, remember how we said we had one president's age was 42 and one president was 43? So this dot right here represents the president at 42. This one represents the one at 43. If you look back at your table, you would notice that there were, I think, 551 ages, 5 presidents aged 51. And so if I'm here at 51, there should be 5 dots. All right, so each dot represents an individual data point. And again, you can sometimes get a feel for the shape of it. I don't know, I get a better feel using a stem and leaf and a histogram, but I can at least get the distribution or how the range of my data from it. Again, like the other one, I can see that the smallest data point is occurring at 42. The largest one would be up there at 78. It kind of also identifies for us what we're going to call outliers, right? So you can see that there's this big gap right here, which is kind of unusual. right? That one right there. Okay, so it kind of tells us little bits of information about the data set we're looking at. Okay, now I'm going to let you write down that information about a dot plot, but before I leave this graph, I want to go back and discuss one other thing I forgot to say. Remember how we talked about the bin width and how I can adjust the bin width? Now, I played around with the bin width using that applet, but that's not the way I would normally do it. If I was asked in a homework question to construct a histogram with a certain size bin width, right? I'm gonna go to the histogram graph, just like you would normally do, but down here, you'll see I now have the option to adjust the bin width. So if I wanted to say, and it will tell you in your homework where you want to start it at, I'm going to say start at 40, and I want a bin width of 2. That's the same histogram we were playing with on that slider one, okay? So if you don't do anything with the bin width, it's going to automatically create a histogram based on, I guess, the most appropriate distribution. And that's what I would default to. Go with that one. Only adjust your bin width if you're asked to in a problem, which is the only time I would ask you to change it, okay? Okay, so to write down some information then about a dot plot, we have this. Remember that our dot plots, each dot plot represents an actual data or observation. I would say sometimes it is going to have the same shape as a histogram, as the histogram would. You can do it rather quickly without using technology if you were doing this by hand. So that would really only be useful for smaller data sets. Okay. Now I keep telling you that the goal of our quantitative data, right? The goal of our quantitative graphs, the ones that we're choosing, is to be able to identify certain characteristics about that graph. And so what we have here is 4, I'm going to add a 5th shape up here. You need to write these down someplace else, not on the back of this paper, someplace else on another sheet of paper. Sorry, I didn't add it onto your notes. Because these shapes are really important. We will keep coming back and asking what the shape, the center, and the spread of our distribution is based on these characteristics we're learning right now. So what we have here are 4 examples of histograms, and we are going to come up with a name for these particular shapes. The top left-hand corner up there, that is a uniform distribution, okay, or a uniform shape. The characteristics there are that the height of our bars are roughly the same. Now, this picture up here is simply, that's a perfect world right there. And you don't always have data that comes in a perfect world. What you're looking for in the shape of your distributions are, in general, does it meet these characteristics? So this characteristic over here for uniform are that the bars are roughly the same height and that it's symmetric. Now, what does it mean to be symmetric? If I were to take the center of this graph and fold it in half, it would be the same on both sides. So a uniform distribution is symmetric and the bars are all roughly the same height. The next distribution, moving over to the top right side, is called bell-shaped, and I would ask that you add in there the word normal, because we're going to change our vocabulary in like a chapter. And we're not going to call it bell-shaped very often much more, we'll call it normal. But they're synonymous, they mean the same thing. A normal distribution, the characteristics there have that single peak in the middle of your graph, followed by tails on either side, okay? So I have this single peak in the center, and I have tails coming down on either side. Now, a normal or a bell-shaped distribution is also symmetric. So if I were to find the center of the graph and fold it in half, it would look roughly the same on both sides. Now, how many of y'all have ever heard of grading on a bell curve? Y'all heard that before? Okay, so think about this for a second. Y'all look up here for a minute, okay? Think about this for a second. Our letter grades are A, B, C, D, F, right? So you have 5 letter grades. And if you're grading on a bell curve, what that says is the middle grade of a C is supposed to be average, right? That's supposed to be the average grade. That is the value that you would have the most data in. The most grades in your class would be in the C range. Then as we move to the left of that, we would have fewer B's and even fewer A's, okay? And then if we move to the other side, we would have fewer D's and even fewer F's, all right? So on a grade, if you grade on a bell curve, what you're saying is the majority of my grades are going to be here in the middle. Notice that the height of my frequency bars are tallest in the middle. Remember, that means that's where most of your data is at, right? Those are the values that are the largest. The taller the bar, the more data is in that bar. It has the largest frequency in that bar, okay? The smaller the bars, the less data, right? There's not as much data contained in those bars. So for a bell-shaped distribution or a normal distribution, you have that central peak in the center, followed by the tails on both sides, and it's symmetric. Now, these two that are down in the bottom, one is skewed right and one is skewed left. Imagine if I were to just sketch a curve above this graph, I would sketch it above it and then I would extend it off, moving into this section over to the right, into the tail. Now, this tail is to the right, isn't it? The tail moves to the right, and therefore we call it skewed right. Okay? The skewed data is easier to understand its naming based on its tail. So with a skewed right data, with a skewed right distribution, you have less data in the tails and more data at the front end. Switching that around with a skewed left distribution, you have the tails pointing to the left, isn't it? Can you all see that the tail on the skewed left is pointing to the left? Okay, so I have less data here growing to more data at the end. All right. So for a skewed right distribution, that's an example of average house prices. Okay, so if you think about home prices, all right, you've got home prices that are they're gonna start out low. They'll increase to your average price about here, where the majority of home prices are, and then you're gonna go down because that's when you get into maybe more expensive houses, but there are less more expensive houses. There's fewer of them, right? Coming all the way out here to maybe some of those gargantuan mansions, but there's not many of them, are there? All right, the majority of your data is over here, and it moves out to the tail where you have less data. All right. Skewed left, an example of skewed left data has to do with our COVID numbers. right? So think fatalities, that's the easier one right there, right? COVID fatalities impact who more often? Older people, right? So if you're thinking about that, if you have younger ages here, it just increases until you get to the older people over here, all right? So that's an example of a skewed left distribution. Okay. Now, it's very, very important that you understand this information right here, okay? So what I want you all to do, hopefully you have that information written down. What I want you to do is turn your paper over to the back. And on the back of your paper, you see that you have a column that has a category name, okay? Oh, one more category that we need to talk about is bimodal. So I would add this one, okay? Bimodal. A bimodal distribution. A bimodal distribution is also symmetric, roughly, but it will have two distinct peaks. Right? Two. These peaks don't have to be the same height, but you've got two distinct peaks. Okay? All right, so that paper that you're working on the back of that paper is a column for categories, a column for description, and then a list of graphs. So we're going to work in groups of 2s and 3s. What I want you to put in the category name are the 5 graphs that we just talked about. I know that there's 6 rows there, but just ignore the last one, okay? There's 5 graphs we just talked about. What are they? Uniform bell,
Skewed right and left.
skewed right, skewed left, and bimodal. That's 5. Now, next to that, you're going to write down a description in your own words of each of these 5 categories, okay? And then after that, you're going to take this set of cards that I'm going to give each group, and you're going to match the card with what you think its category ought to be in, okay? All right, so I'm going to come around. I'm going to put you in groups of 2s and 3s. I'll let y'all be in group 2. I'm going to let you two George, Lauren, work together. Okay. You 3, you can work over here, okay? And work over here.
I was about to say.
Oh, okay, y'all can work
Which
together.
gets.
It's like, we pretty much just like,
Yeah, you're actually
we're
worrying
trying,
about where the
I ain't gonna lie,
some of it I know.
most data is
It's
not
like
detailed. Most data is
uniform, bell
shifted
shape,
away
skewed
from
right,
detail.
skewed left.
Okay.
and flat skewed.
All right, so you've got about 5 minutes to get this finished,
Bimodal.
maybe 10.
It's like it's up on the board.
For bell-shaped, how would you describe a bell-shaped distribution? What are some of the characteristics we're looking for? Single peak in the middle, what else?
Slightly symmetric.
Symmetric, right? Single peak in the middle, symmetric. All right, and for bell-shaped, what graphs would you have? Did you write the names of them down?
ACT scores.
ACT,
IQ.
IQ, and some of the dice, okay? Now, the reason I want you to write these names down and not just the numbers is if I ask you to give me an example, or maybe you need to identify an example of something that is skewed, symmetric, normal, you've got an idea of what that data would look like, or what kind of things are we looking at? How about uniform? What are some characteristics for uniform? Mostly the same height, right? And symmetric. Mostly the same height and symmetric. What two do we have for that?
Die roll and random numbers.
Random numbers and die roll. Okay, die roll, single dice roll, right? Single die. So if I roll a die, a single dice, I've got an equally likely chance of getting a 1 as I do a 5. Okay. Skewed right. What did you say for skewed right?
Data trails off, right?
Okay, the tail is off to the right. The majority, so less data to the right, majority of the data to the left. Very good. What values do we have for skewed right? What graphs?
What time can we come and student ages?
Wait time, income, student ages, and one more.
The number of children.
Number of children, that's right. Number of children. All right, how about skewed left? Well, that would be just pretty much the opposite of skewed right, correct? Tail goes to the left, majority of the data is to the right. What do we have for skewed left?
Weight and grades.
Weight and grades, very good. So then the last one has to be bimodal. How do you describe bimodal?
Two distinct peaks.
Two distinct peaks and it's symmetric. Okay, it has symmetry. And which one did you have for that one?
Height and number of children.
Nope, just height. Now,
Just height.
why is height bimodal?
Number of children.
Why is height
Because
bimodal?
Different average heights for male and female.
So if we were to take our data set, right, our data set where you were supposed to answer the height in inches, and it's mixed men and women who did the submission right there, right? You have an average height for men, you have an average height for women. So if that data set is grouped together, you would have two distinct peaks. The peaks would not be the same, right? Because the average height for men is not going to be the average height for women, but you would have two distinct peaks. So height, where you're not separating it out, would be an example of a bimodal distribution. Okay, now before you leave, I have 2 minutes left.